In section 2.3, we'll learn the graphs of the secant and cosecant functions. Now, even though the graphs of secant and cosecant can be somewhat intimidating because they contain vertical asymptotes, the good news is the better you know your cosine and sine graphs, the easier secant and cosecant will become. Let's examine the graph of secant. Recall that secant and cosine have a reciprocal relationship. That is, secant of x equals 1 over cosine of x. So if cosine of x is equal to 0, then secant of x would be equal to 1 over 0. That's an undefined value. So wherever cosine is equal to 0, secant is undefined. This means that everywhere that cosine of x has an x-intercept, y equals secant of x will have a vertical asymptote. So let's examine the graph of one fundamental cycle of cosine here down below. Everywhere that cosine has an x-intercept, specifically pi over 2 and 3 pi over 2, you can see that secant has a corresponding vertical asymptote. So every x-intercept of cosine of x is going to yield a vertical asymptote for secant of x. Similarly, observe that if cosine of x has a value of either positive or negative 1, then secant of x has the reciprocal value. Well, the reciprocal of 1 or negative 1 is also 1 or negative 1. So when cosine has a value of 1, secant has a value of 1. When cosine has a value of negative 1, secant has a value of negative 1. So notice the secant bounces right off of the cosine wave. Now, because they have a reciprocal relationship, we could see that as cosine of x approaches its x-intercept, that is the value of 0, then secant of x is going to go the opposite way. Secant of x is going to approach infinity. So notice as cosine approaches its x-intercept here, secant goes the opposite direction. We can see that in this perspective as well. As cosine approaches its x-intercept here, secant goes in the opposite direction. Now, the graph of secant only consists of these little parabola shapes and half parabola shapes. There's one fundamental cycle of secant. But understanding that in context or in relationship to the cosine wave will make the graph easy to execute. Like cosine, secant has a period of 2 pi. And understanding that secant is going to have a vertical asymptote everywhere that cosine has an x-intercept, we can write an equation for every single vertical asymptote of secant in a formulaic way. So notice the first vertical asymptote occurs at x equals pi over 2. Then, pi units later, we have another vertical asymptote. Then, pi units later, there would be another asymptote. So for every multiple of pi added to that first asymptote, we're going to land at another asymptote. So we could say the asymptotes are located at pi over 2 plus some multiple of pi. Now we need to specify here that k is an element of the integers. So this little symbol is from set theory. It represents the phrase is an element of. So k is an element of, and this is the symbol for the integers. You may have seen the r with the double bar at the left representing real numbers. When you see the z with the double bar, it represents an integer. So k has to be an integer multiple of pi. I don't want to add a fraction multiple of pi to pi over 2 because then I would not arrive at an asymptote. Now, the domain of secant is going to be everywhere except where those asymptotes occur. So the best way to describe the domain of secant is using set builder notation. Interval notation is pretty difficult when you have an infinite number of intervals. So we're going to say the domain is the set of all x such that x is not equal to the values of these asymptotes, pi over 2 plus k pi, and it's necessary to specify that k is an integer. Understanding that secant sort of envelopes cosine, the range comes in two pieces. The bottom half of secant has values from -infinity to -1, and the top half of secant ranges from 1 to infinity. So we're looking at lowest minimum value for y is -infinity, and then it's going to stop at this maximum value of -1, and then there's a break in between. Then we have the value of y equals 1 on up to infinity. So the two separate intervals in the range of secant correspond to the lower and upper halves respectively. Now, understanding that fundamental cycle for secant, then all of the transformations that we've learned for cosine may also occur on secant. So let's try example 1. Graph one cycle of y equals 2 secant of x. Now, in order to graph 2 secant of x, I'm going to compare it to y equals 2 cosine of x. If I can generate the graph of 2 cosine of x, and I can remember that secant and cosine have that reciprocal relationship, then we can simply bounce the graph of secant of x off of the graph of 2 cosine of x. Now, 2 cosine of x has a period of 2 pi, and notice the amplitude there is 2. So I'm going to use 1 tick mark per unit to label my scale on the y-axis. And I'm going to begin by sketching the graph of cosine. One fundamental cycle. Now, because the amplitude is 2, cosine is going to begin its bowl shape and end its bowl shape at y equals 2, and then right in the middle, it's going to have the minimum value at the point pi -2. Halfway in between each of those points, cosine crosses the x-axis. So here's the sketch of one fundamental cycle of 2 cosine of x. Now I'm going to clearly label that so I can distinguish it from the graph that I'm actually trying to execute. Now, everywhere that cosine of x has an x-intercept, secant of x is going to have a vertical asymptote. So the first one occurs at pi over 2, and the second one occurs at 3 pi over 2. And notice the distance between those asymptotes is half of the period, or pi unit. Now, everywhere that cosine of x has a value of 2, secant is going to have that same value. Remember, secant of 0 is equal to 1, so 2 times secant of 0 is equal to 2. So everywhere that cosine hits a maximum or a minimum, secant is going to bounce at that location. And then remember, secant goes in the opposite direction of cosine. So I'm going to form the graph of secant just as a sketch here in between the boundary lines of those asymptotes. So the gray curve there is 2 cosine of x. The green curve is 2 times secant of x. Now, the period of secant of x is 2 pi, just like it is for cosine. Because there was no horizontal transformation here, the asymptotes for the entire secant curve, not just the fundamental cycle that I've graphed, but the entire secant curve would be at pi over 2 plus a multiple of pi on either side. So I could add a positive multiple to get asymptotes to the right. I could subtract a multiple to get asymptotes to the left. The domain of secant then is the set of all x such that x cannot equal those asymptotes. At those asymptotic locations, secant is undefined. As for the range for this specific secant function, the lower half ranges from -infinity to -2. The u in the middle of the intervals represents union, and then we're going to range from 2 to infinity for the upper half. Now, if you want to graph this on your calculator, remember that you don't have a secant button, so you're going to have to type it in as 2 divided by cosine of x. So when you graph 2 divided by cosine of x, here you can see a couple of fundamental cycles of the secant curve. It's also helpful to visualize its relationship to 2 cosine of x. So if you want to graph that on your calculator as well, just be sure that you are in radian mode to see that graph. So once again, the better that you know the graph of cosine, the easier it will be to generate the graph of a corresponding secant. Let's practice another example. Graph one cycle of y equals negative secant of x plus pi over 2. So to figure out this graph, I'm going to consider its corresponding cosine wave. I want to graph negative cosine of x plus pi over 2. First, notice that we have a reflection across the x-axis because of the presence of this negative. In addition, we have a phase shift left by pi over 2 units. Now, because there's no amplitude change on this function, I'm going to use 2 tick marks per 1 unit to sort of spread out my graph here. To figure out the beginning and the ending of one fundamental cycle of cosine, I'm going to recognize that the argument, x plus pi over 2, needs to range between 0 and 2 pi. When I solve for x, I end up with the interval negative pi over 2 less than or equal to x less than 3 pi over 2. 2 pi minus 1/2 pi gives us 3/2 pi. So this means when x is equal to negative pi over 2, cosine normally reaches its maximum, but again, because we're reflecting this across the x-axis, it's going to reach down to a minimum of -1. At the end of this interval at 3 pi over 2, it will also reach its minimum at -1. Halfway in between those values, now remember that location can be obtained by finding the midpoint of these two guys, add them together and divide by 2. 3 pi over 2 plus negative pi over 2 is 2 pi over 2, or pi, and then divide by 2 to get pi over 2. Or notice, if I count to the center, 4 units this direction, 1, 2, 3, 4 units this direction, I'm going to land at that midpoint. So here in the middle, cosine is going to reach its maximum. Then halfway in between maximum and minimum, it crosses the x-axis on either side. So the fundamental cycle of cosine of x that I'm going to use to generate the secant looks something like this. Now, everywhere that cosine of x has an x-intercept, secant is going to have a corresponding vertical asymptote. So the first one occurs at 0, the second one occurs at pi. Notice there's a distance of pi units in between those two asymptotes. So secant, like cosine, has a period of 2 pi, but the asymptotes are pi units apart. Now, to express the equation of not just the 2 that we see on the graph, but all of the asymptotes for the entire secant function, we can recognize that the first one occurs at x equals 0. The second one occurs at x equals pi. Then we can anticipate the next one would occur at 2 pi. So notice if I start at 0 and I add an integer multiple of pi, I'm going to land at another asymptote. So instead of writing 0 plus k times pi, we can shorten that simply to k pi. So at every integer multiple of pi, secant is going to have a vertical asymptote. Remember, k and z is essential. Now, if I can find the locations of those asymptotes, I can specify the domain by saying that the function is defined everywhere except those asymptotes. So the domain indicates x cannot be equal to those values. Now let's go ahead and bounce secant off of our cosine. Remember, secant and cosine are going to share their maximum and minimum values. Secant is going to approach the asymptote going in the opposite direction of cosine. So over here, we're going to get half of one little branch going this direction and the other half going this direction. So just the green curve there is the graph of secant. With that sketched, we can observe that the range goes from -infinity to -1, and then united to 1 to infinity. So to graph a secant, I highly recommend graph the corresponding cosine wave first, locate the vertical asymptotes of secant by identifying the x-intercepts of cosine, and then bounce your secant curve right off of that cosine curve. Makes it pretty simple and straightforward.